In this question down here, we're asked which of the following best describes the molecule shown here. Does it possess one chiral center, two chiral centers, is it achiral, or is it a meso compound? The correct answer is option B. If you'd like to know why, I'll explain it for you right here on the board.
This question asks us how many stereocenters are in this compound, or is the compound meso? Remember, a stereocenter is a tetrahedral atom. For all of your organic classes, that's just going to be carbon, although there are other atoms that can attain tetrahedral shapes. Anyway, a tetrahedral atom that has 4 different groups around it. So we're going to look for those, scanning from left to right. I've got a carbon, a bunch of hydrogens on it, doesn't apply. Here I've got a carbon, it's bound to a hydrogen pointing out back and oxygen pointing towards us, a carbon to the left and a different kind of carbon to the right. That is absolutely a stereocenter. As I go here to the right, I've got another carbon atom that's bound to an oxygen pointing towards us, hydrogen pointing away from us, and a carbon to the right and a different kind of carbon to the left, also totally a stereocenter. There are 2 stereocenters in this molecule. Now I want to throw a hypothetical at you. I want you to imagine that instead we had this molecule. While going through the same logic, we might conclude that it also has 2 stereocenters, the ones that I've asterisked here. There's a problem with this molecule, and hopefully you can see it. You can see that if you bisect this molecule right down the middle, everything to the left half of that line is a mirror image of everything to the right half of that line. Because the mirror image is staring in the same molecule at its reflection, this type of compound would be meso and hence would be achiral. How many stereocenters are in a meso compound? Well, I don't know. Technically, you could still consider those stereocenters, but it is not going to be chiral. That would be a meso compound. Just wanted to throw that at you, shake things up a little bit.
In this question, we're asked which of the molecules shown to the right is a Z-alkene. The correct answer is option C. If you want to know why, I'll show you why here on the board.
Here we have to decide which of these molecules is a Z-alkene. Now remember how you do this. You find the carbon-carbon double bond, draw a squiggly line down it, and it doesn't have to be squiggly, but it's preferable for me. And then look to the right and to the left. As we look to the right, we have to determine which of these 2 groups, the chlorine or the oxygen, has higher priority. The highest priority is determined, or I should say priority is determined by the highest atomic number. Who has a higher atomic number? Chlorine or oxygen? Chlorine does, which means this is the highest priority, which I'll indicate by writing the letter H. Now I look to the left of my squiggly line. I've got a carbon and a carbon. Who has a higher priority? Well, they tie, so I have to keep going out until I break the tie. This carbon up top is bound to hydrogens. This carbon down at the bottom is bound to another carbon, which means that carbon has, of course, a higher atomic number than hydrogen. So this lower chain or branch is called, this lower chain or branch is the higher priority. I'll put an H by it. Is this molecule an E or a Z alkene? Remember, if both of the highest priority groups are pointing in the same direction, that is, if they're on the same side, both pointing up or both pointing down, it is a Z alkene. They're on the same side, Z. If they're pointing in opposite directions or opposite directions, then it is an E alkene. Here's my highest priority, here's my highest priority. Are they both pointing up or both pointing down? No. One of them is pointing up and the other is pointing down, which means they're on opposite sides of each other, so this is E. Please excuse my incorrect English. I just use these sort of mnemonics to help me remember things. So, let's do the same thing over here. Squiggly line down the middle of the carbon-carbon bond. We'll look at the groups on the right. I've got a bromine and a hydrogen. Bromine wins. He's the highest priority. We'll look at our groups on the left. I've got a carbon and a carbon. They tie. I go out to break the tie. This carbon here is bound to some oxygens. This one's bound to hydrogens. Carbon to the on the bottom is the highest priority, so I'll write H here. I've got an H pointing up. Bromine, and I've got an H pointing down, this carboxylic acid group. One's pointing up, one's pointing down. They're on opposite sides of each other, so that is an E alkene. Let's take a look over here. I'll go ahead and draw a squiggly line down here. I've got my groups on the right, chlorine and oxygen. Who has a higher higher atomic number? It's the chlorine, so he is the higher priority group. Groups on the left, I've got a hydrogen and a carbon. Carbon wins, which means this whole branch is considered the higher priority group. One's pointing up, the other's pointing down. They're pointing in opposite directions or opposite directions. Hence, that molecule is an E alkene. Now we'll look at this one. Squiggly line down the middle. I've got a carbon and an oxygen. Who wins? Oxygen wins. Now this might be confusing to some people because they might see that chlorine and think, chlorine's way higher in atomic number than oxygen, so chlorine must win. But remember, we broke the tie right here. There's a carbon and an oxygen. Oxygen has a higher atomic number than carbon. The tie's broken. It is done. It doesn't matter if there's a Lamborghini attached to this carbon after that. We've already broken the tie, which means that this OH is the higher priority group. Let's take a look at the groups here to the left. I've got a hydrogen and a carbon. Carbon wins, which means that this group pointing down here is also the highest priority group. I've got my highest priority group to the right pointing down, highest priority group to the left pointing down. They're both pointing in the same direction. They're on the same side as each other, which means that this is our Z alkane. Oh, and by the way, you don't have to write exclamation points after the Z or the E. I just do it because it's kind of fun.
In this question down here, we're shown these different molecules, A through D. This question asks us which of the molecules shown here are diastereomers. And the correct answer is A. If you want to know why, I will explain it to you on the board right now.
Now, I've said this before, maybe too many times, but repetition never hurts anybody. If you have stereocenters in molecule A and molecule B, and the stereo configurations at each of those stereocenters are exactly opposite, then molecule A and molecule B are enantiomers. If you have molecule A and molecule B and their stereocenters are exactly the same, then molecule A and molecule B are the same molecule. Now, if I have anything in between, then molecule A and molecule B are diastereomers. So let's take a look at this. All these molecules look exactly the same as each other, except their stereo configurations at their individual stereocenters, which I'll put little check marks next to. In this case, I've got a stereocenter where I've got a dashed bond here, and here I've got a wedged bond. Over here, I've got a wedged bond and a wedged bond. Over here, I've got a wedged bond and a dashed bond. I've got a dashed bond and a dashed bond. So who are exact opposites of each other? Well, over here, I've got a dashed bond to the left and a wedged bond to the right. Who's the exact opposite of A? Well, down here, I've got a wedged bond to the left and a dashed bond to the right, which means that A and C are enantiomers of each other. Hopefully that makes sense. They're exactly opposite. I'll go ahead and abbreviate that by saying or writing enants. Yeah, don't do that on your tests or anything, by the way, but I just do it because of laziness. I don't want to write the suffix eomers. I'm going to have to take a nap after I do that. Anyway, okay, let's go over to this one. Over here I've got a wedge and a wedge. What would the exact opposite of that be? Well, it'd be a dash and a dash, which means that B and D are also enantiomers. I'll write enants. Once again, B and D might not look enantiomers the way they're drawn, but if you took D and flipped it upside down like a pancake and had it stare in the mirror, it would see molecule B. What are these things all relative to each other? Well, okay, A and B. I've got a dash here and a wedge here, and I've got a wedge and a wedge. A dash and a wedge and a wedge and a wedge. Are those exact opposites of each other? No, they aren't. They aren't exact opposites. They're somewhere in between, which means that A and B are diastereomers of each other. I'll go ahead and write diasts. Okay? Okay. What about C and D? I've got a wedge here and a dash here, and over here I got two dashes. Is that exactly opposite? No, it's not, which means that C and D are also diastereomers of each other, diasts. Okay, so I've got A and C being enantiomers, B and D being enantiomers, these guys being diasts and diasts. So let's see if any of these things match what we've said. The question is asking us which of these sets of pairs of molecules are diastereomers of each other. Are A and B diastereomers of each other? Yes, they are. Are B and D diastereomers of each other? No, they're not. They're enantiomers of each other. Are A and C diastereomers of each other? No, they're not. They're enantiomers of each other. So the correct answer is A.